Hi,
Hi.
and welcome back to TezAsia Hackathon. So, on today's 17th of August, and we have a special guest, Mike. He's from Cryptonomics, and he's going to go through a workshop called Connecting Smart Contracts with the front end and signing transactions. So thank you, Mike, for coming down in this time to actually to go through for this workshop. So I will pass the mic back to you. Thank you.
Thanks for the intro, Brian. I'm very happy to be here. Yes, so today we're going to continue working with the DAO contract that we've been building over this series of talks. Those of you who joined me for the previous two conversations would have seen this contract already. This is the unmodified named contract. Interestingly, as I was testing it for this presentation, I found a small issue in it, uh, which was not accounted for in the tests. Specifically, it was this line, be greater than or equals to load balance. But I did deploy this contract as is, so that it's consistent with what you guys have seen previously. And let's actually talk about how that was done. So Tezos has a rolling protocol upgrade process. So we just had an update recently, and we're now on Granada net, but there's also a testnet for Granada. And of course, you can get testnet coins. And you would do that by going to the Tezos faucet. It's like this, check a box, and you get an address. Now, today we're talking about how to connect smart contracts to front ends. I do not have a deck for you because we're going to be writing code the entire time. So this is what this stuff looks like, and we're going to go over that in a moment. But first, let's talk about how SmartPy already helps you do some of this stuff. So as I mentioned previously, there is a uh, full simulation set, a functional set in SmartPy. So when we do the tests, we actually get the execution of absolutely everything that this contract does and everything that we're testing explicitly as defined below. In addition to that, SmartPy can deploy a contract for you. To do that, first you need to configure a wallet. And I already have a couple of accounts added here. So previously, I grabbed a faucet account, copy that, drop it in here, and we just follow the steps. Save. We're going to be deploying to GranadaNet. You can use SmartPy or why not. Activate the account. So the account activation process is only required for two types of accounts. It's either a faucet account or the fundraiser account, of which there are fewer and fewer left. So when Tezos launched originally, it did so through a fundraiser process. Some number of accounts were created in the Genesis block. So similarly, the testnets operate with faucets. These accounts have to be activated. When you create a new account separately, you do not need to activate it. And once the account is activated, we will need to reveal it. Revealing you have to do for every account. And what the reveal operation does is it publishes the public key of the account to the chain. And the reason for that is so that nodes can confirm that operations signed by this account were indeed signed by verifying the signature against the public key. And of course, the private key should be kept secret. These are false accounts. So. Right. So after activation, keep in mind that Granada net block time is 30 seconds. So most certainly this activation would have been recorded by now. We can, of course, double check this. And there are several block explorers available on Tezos. One of them is Aranex. Well, Aranex is a cryptographic product that I mentioned earlier, and this is more of a data reporting tool than a block explorer, but I did not do it before. I could not afford it. But it can do queries like this as well. So here we have the activation that was already completed. Very good. We can reveal the account, and then it will get revealed. The public key will get published. So great. We have an account that we can use. Now we can deploy the contract. Not sure why this comes up. I haven't had a problem deploying a contract regardless. So we're going to ignore that. We use a faucet account from storage. This is the one that we just added. Not mainnet. This is right. And so you see that the account has 19,000 play Tez. Very good. Now estimate cost to RPC. What this does is it pre-applies the operation, pre-applies the actual RPC call. It effectively simulates the operation against the node. In this case, we selected the SmartPy node. We'll talk about what other infrastructure you can use as well. So according to the node, this operation will take 003 Tez to execute. There's a gas limit, there's a storage limit. These are tight estimates. You can use them most certainly. In Conseiljs, there is a default pattern just in case. So I normally add a little bit of gas and a little bit of storage for every operation, just in case it changes. Now, why would this ever happen? Gas is the effectively measure of computational complexity of a contract. So if a contract operation looks at chain state changes and can potentially impact the way the contract executes, in which case you might actually have to spend more gas. Now, this is a contract deployment operation. In Tezos terms, it's called an origination, which is why you see that here. Originations are unlikely to require additional gas, but nonetheless, a good practice to increase the gas limit slightly. Storage limit is similar to gas limit, where it is a cap on how much storage you can use. Keep in mind that while gas limit is accounted for in the fee, storage limit is not. So storage cost is taken out of the account separately when the operation is executed. And it doesn't, just because you set storage limit to this number, it doesn't mean that this is how much will actually be used. Right, and then we click deploy contract, and it'll do its thing in contract and get deployed. I have already deployed one. And we can take a look at it here. Now, for development purposes, Better Call Dev is quite good. So this is the contract address that I deployed earlier. Run my test script against it. As you can see, I have a couple of operations. I did this just a few hours ago. Very good. Now, this is the Michelin representation of the contract. How do we know that? If we look here in the code JSON, which is the Michelin representation, we can see that it's the same thing. So we have, for example, a function called claim, and here's a function called claim. Very good. Right, so Conseiljs. Conseiljs is a library from Cryptonomic that allows for smart contract interactions on TezAsia in JavaScript, and also allows for Conseiljs interactions. So you saw earlier Aronex. That's actually an example. Very good. So right now we're looking at some number of most recent blocks. Aronex is a indexer, and you can query it using JSON, and there's an interface with this in Conseiljs. So Aronex is built in Conseiljs. And when we look at the console prints every single query that it executes. So here you can see the query that went out to the server. So we see, for example, timestamp, period, cycle, level, baker, block, hash, priority, right? So you will see these things appear here: timestamp, period, cycle, level, baker, block, hash, priority. And this is possible through Conseiljs. But also, of course, we would like to be able to interact with smart contracts, and Conseiljs does that as well. To do so, we most certainly need to be able to manage keys. We need to be able to submit other kinds of operations like activations and key reveals. So the same process that I just showed you in SmartPy is indeed possible in Conseiljs. So let's review that real quick. I have 2 faucet accounts that I loaded previously, and this was my test script, so I have already run these operations. Let's take a look at what a init faucet account does. It will, first of all, read a JSON file, which is just that, and then restore identity from fundraiser. In terms of the testnet, fundraiser would be the faucet. And it takes a bunch of parameters, namely the mnemonic, the secret, the key, the public key hash, password, email. So these are just passed as parameters. We print to the console what we're looking at, and we create a signer. So blockchain operations need to be signed cryptographically. We're using Sodium to sign these operations. And this is the line that allows us to get access to that signer. And then we'll be submitting operations. So first, we saw earlier, we have to activate the account. So we take the signer, the key store, which is effectively the private key and the public key, and the faucet secret, which is this, which allows us to activate the account. And then we need to reveal the account, and after we're all done, we return the key store. Very good. So what does activate account actually do? First, we check that the account has been previously activated. If it has been, there's nothing to do. If not, we will send an activation operation, which takes a Tezos node, the signer that we created, the key store, and the secret parameter. And what that will do is it will send this operation to the node and return a operation ID. And with this operation ID, we can use Consei to wait for it to get recorded. So what this function does, await operation confirmation in Conseiljs, is it uses Consei, the indexer, to wait for the operation ID that we just recorded. Well, I'm sorry, we did not record it, we proposed it. So when you send an operation to a blockchain, it is proposed in the mempool, and there's some possibility that this operation will not be included for various reasons, like insufficient gas, insufficient fee, perhaps the state of the blockchain has changed somehow, so the operation would get rejected. Various reasons. So when we submit an operation, it's not a guarantee that it's going to get recorded. So what we need to do is wait for it to finish before we can proceed to the next steps, and that's what this does. So we need a Consei server reference, the network, in this case GranadaNet, group ID, which is the operation group ID that we got from the node. 7 here is the number of blocks to wait, and network block time is right here, it's 30 seconds plus 1, just as an offset to wait for every block. Now, how do you get a Consei server? Very good. Among other products, Cryptonomic offers an infrastructure service called Nautilus Cloud. And there is a free service there you can sign up. You log in with your GitHub account. So you can see I'm Sprocket on GitHub. And here is the testnet configuration that I get. And this gives you access to both testnet and mainnet infrastructure. We're using GranadaNet today, so here's the Consei Granada server, and here's the TezAsia Granada server, testnet server from Nautilus Cloud. So when we look at code, we have these 2 lines, TezAsia Granada Cryptonomic Info.tech, and the same for the Consei server. The API key is yours. You should keep it secret. If for some reason you check it in, there's a way for you to reset it. This button here, you can just regenerate the key. Very good. So this will query Consei until it sees the operation. This function is coded in such a way that it will fail after it has seen 7 blocks, so that you don't wait for it. Assuming this succeeds, move on to reveal. Same idea. We check if the account has been previously revealed. And then we send the key reveal. We get the group ID, and we await for this group ID to be recorded on chain. In Tezos, individual operations do not get a reference. What gets a reference is an operation group. So you have this operation group hash. And an operation group can contain multiple operations, which is actually quite useful. So you can execute multiple independent things as a bundle together, and they're executed atomically, meaning that if the first operation fails for some reason, subsequent operations will not be processed. And this is the thing that we wait for to be recorded. Now, in this case, the operation group in both these cases actually includes only 1 operation, but it is possible to include more than 1. Very good. So after this is done, we have accounts that we could use. I have recorded the secret keys that those 2 accounts are for, along with their addresses. Now, init account is a local function that I wrote. It basically says, give me all the bits that I need to be able to submit operations, which is the key store. Again, the key store is just a container for key information, public and private key, public key hash as well. Signer, which is a sodium-based cryptographic signer built with the secret key that we just created here. And counter, something that we get from the node. Counter is a nonce, effectively, replay protection mechanism for the account, and it says that it's a random number that's generated when the account is revealed, and every subsequent operation must increase the count. Now, this is important also in the context of operation groups. Each operation in the operation group has to have its own counter, and this counter is monotonically increasing. So the first operation would have counter that we get here. The second operation would be +2, and so forth. So the counter that you get from the node is the current counter. So to submit the next operation, you have to increment it by 1. So this returns effectively the next counter. Very good. This is an example of a simple operation. In this case, transaction. So what this does is it sends a balance from one account to another account. So we perfectly. Here we go. So what this function call would do is it would take 5xtz. Keep in mind that balances in Tezos are expressed in mutez, meaning 1/1,000,000th. So 5 million here is actually 5xtz. So this function call would take 5xtz from the DAO origination account and send it to signer A account. Public key hash is the address. Very good, just an example. And I will post this code later today so that you guys can run it yourselves and use it as a reference. Key reveal we actually covered. So very good. Now, what else does Conseiljs do? It also allows you to query blockchain data from storage. So the DAO has a storage structure associated with it, and we should be able to read it, right? So this is interesting. Let's go to better call type. So there's a storage tag here, which gives us the contents of storage that are currently recorded. But to get this programmatically, how do we do this? So first of all, storage is available on chain, and all of these RPCs are quite well documented. Their documentation is sometimes lagging current release, so the docs could be somewhat out of date, but this is an old RPC, so everything is good. So we're looking at the Granada Tezos server. That's the Tezos node. This is the contract that we deployed earlier, and we want the storage. And what this gives us is the JSON representation of the storage. So here is the rendering of the same thing. Right, so we want to be able to parse this programmatically. Now, for this purpose, I like to use this library called JSON path. It's like XPath, and it allows you to query JSON knowing what the structure is to get out specific values. So, for example, there's a online calculator for this that you can use. The library is here. So here's our storage, and we want the name. So how do we get the name? So this is root. Syntax is really simple. This is the 0th index of the args attribute that we want to go in. In here, we again want args, and the name is the 3rd element, and we want the string attribute of that, and here we go. So now in the code, we get contract storage, which then takes the node address, and the node address and the contract address. And this is the JSON structure. Here, like this function right here does exactly this. That's it. That's all it does. So now we can parse it using the path we calculated here. and we want the 0th element. So it's possible that, you can see that it's an array. It's possible there'll be multiple values, and we want just one. Very good. Now, of course, we can also call contracts. So let's do some of that. In Tezos, there are two ways to represent both contracts and invocations, and you can see that here. So Michelson is this Lisp style representation, and then Michelin is the JSON version of that. So let's parse this a little bit. Left, left, left unit. What does that mean? So let's take a look at the actual contract. The functions are defined in the parameter section. Let's grab storage. So we're going to talk about functions. So parameter. Have or unit claim. So left, 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 unit. Unit is the equivalent of null in Michelson. So the claim function in the contract does not take a parameter, right? So when we call claim, all we do is we send a test balance to generate a token amount. So we don't pass any parameters, and that's what unit is. Left, left, left allows us to navigate the cone. Now, it is possible to create functions in the contract that are unnamed. This annotation, %claim is an annotation for a function name. It will work perfectly fine like this, but it is more difficult to convey meaning. So that's why we give these things names. So there is count, for example, default, propose, refund. Well, default is a special case. Propose, refund, etc. So what we won't use the name, but we don't have to. So if we weren't using the name, we would have to navigate the cone, which would be this left, left, left unit. Or we can use the name. So when we go back to the code, let's uncomment that. Claim is the function name, and here we have prim unit. So prim unit, this is the JSON representation of the parameter, and this is the Michelson representation of the parameter. Very good. Cool. So when we call these functions, what this will do is modify the storage of the contract, this, and create balance records. So I already did this earlier today. So we have two accounts with balances. I ran one of these calls twice, so both accounts actually have the same balance now. And we can see these calls over here. So here's a claim call, account E2S sent in to Tez and received a balance of 2 million tokens. Very good. What else can we do? Propose. Similarly here, we give it a function name and parameters. Oh yes, I'm sorry, I should have mentioned this. So See here we have Teza's parameter format. The JSON representation is Michelin, and the regular representation is Michelin. One more interesting thing on this line is this number 54. So on Tezos, for fork mitigation, ephemeral fork mitigation, which is compared to like hard fork, and ephemeral fork is a temporary disagreement on what the current chain is supposed to look like. So for fork mitigation, you are required to include a recent block hash, and there is a limit to how recent this hash has to be. It's 64 blocks ago. So basically, although that may have changed a lot, I should check. 64 blocks is a little over half an hour. So what does this mean? This means that we want to use a block hash that happened 54 blocks ago. Why would we want to do this? So that if this operation, for some reason, gets stuck in the mempool and doesn't get recorded, it will get expired in 10 blocks. And this is useful because if you have a pending operation on an account, this account cannot submit new operations until this one is cleared. So it's either included, rejected, or timed out. So if we're not being included and we weren't rejected, timeout could take a long time. So we want to reduce this amount of time. Similarly, you can set this to 0, and this will be the head, right? But then if it's going to be head as the current block hash for this operation, it'll take a much longer time for you to time out of the mempool if the operation is not getting good. Very good. So this operation we also executed. So let's run this operation. So this is the code build. I prefer TypeScript. So there are a bunch of little bits that you have to do to make TypeScript work. Maybe this. There's also a build step which transpiles TypeScript into JavaScript, which is going to be one build we'll do. And we do start to actually run the code. So in this case, it's going to just call the run function, and the run function will initialize the accounts and propose an event. So we'll open the accounts, blah, blah, blah. There's a bunch of output that this thing prints, and you can control this here. So Conseiljs requires a couple of things to run. One of these things is fetch. Fetch is a library used for HTTP calls. The reason it's a parameter is so that you can provide your own implementation of fetch. For example, one that is proxy compatible. I'm just using the standard fetch from Node. And it needs a logger. The logger is this log level library that I like. And we're setting level to debug. If we set the level to error, it will print a lot less stuff. So I just do my next operation like this, and you will see a lot less output. But it's dumping a lot of information. So here's the operation that was constructed. It has JSON. Here's the binary representation of the same operation. Here's what the estimates are like for the cost of the operation. And then it sends it in, perform post request, and we have a signature that we created with our private key. And finally, we ship the operation to the node. And one thing I should have done was the same thing that we did here, which is print the node result, which actually contains the operation. In either case, we can see this operation here. With now an active proposal. Very good. So all the stuff I have written previously, let's do another one. Let's use the B account to make a proposal. Let's use the A account to vote. How do we vote? Well, we're going to go back to SmartBank. And in our simulation, we have this very nice, easy to read representation of the state change, but we also have this Michelson tab. And again, we have the parameter and the JSON version of it. So as we discussed earlier, this right here is the navigation to the function that we're trying to call, but the function is called vote. And then we have the parameter, which is this. So we can simply grab that. As you spend more time working on Tezos, you'll be able to encode these simple things yourself. Conseiljs can also encode a large number of these things, although there are limits to how much it can do. So very complex parameters it may not be able to encode from Michelson, but Michelin is a straight pass-through and everything gets encoded correctly. We have lots of unit tests around. Very cool. So this line then is going to have the count A, submit the vote. And that's really that simple. Save it. All right. So as you can see, a lot less output. Now it's really only printing the lines that we have here and nothing else. And it's done. We're done printing. So keep in mind that this invocation here is a bare invocation compared to the wrapped one that was an example here. So we're not waiting for this operation to be completed. We're just submitting it and moving on, which means that if you were to call another operation immediately after this one, if you were to do this, for example, this may fail because the previous operation hasn't been recorded yet and the counter has not incremented, so you're using a bad counter. And furthermore, while the operation is pending, gets something. And we have the separation ID. So I wanted to show you this entire result. This is why there's this function right here. to remove the artifacts. But then we can take this into here. And this is the operation. Cool. And that's really all it takes. So now we have this code, and this code can be hooked into the web application. You can use it in React Native. You can use it in Electron to package a desktop application like we do with Galleon. There are lots more features to Conseiljs. The library is fairly well documented. If you have specific questions, I'm of course available, as are the rest of the team, for questions. Yeah, that's all I have for you today. I hope that was useful, and we have some time left. So if you guys have questions, I'm happy to answer them.
Okay, thank you, Mike. We can wait for 1 minute first. If there's any questions, I will show you on the screen. Okay. Thank you, Mike, for for waking up so early to actually conduct this a workshop actually, and through this connecting the smart contracts to the front end and to sign those transactions as well. So I think it gives like the viewers a more in-depth into how to actually do or conduct these transactions. Yeah. Keys and I do not think there's any more questions actually. So we would like to end it here. So and once again, thank you, Mike. Mike Verdun from Cryptonomics. He's from engineering in Cryptonomics, and it's actually it's a great day that you join us for this workshop and to conduct it. So have a good night on to you as well. So okay, so thank you so much, and have a good day.
Yes, and again, if you guys need help, we can be reached. If you can't find us online, the Tezos India organizers know how to reach us. And thanks again for inviting me.
Okay, thank you. Have a good evening. Bye bye.
Bye bye.